Hello.
Hi. Hi.
Hey, how you doing?
Uh, good. How you doing?
Good. I was using the other link from the email, so that's why I'm a little bit confused. But
Uh,
I kind of sorted this out.
Wait. So this is interesting. Oh, I think the same thing happened to me as well. Which link? The one which is in the email?
Yeah, so there is one link in the email, there is another link in the PDF file. So this room is for the link in the of the PDF file, but the link in the email is something wrong. It's something else.
Oh, okay. Let me actually, maybe that's why people are actually not able to show. Let me let me fix that.
Sure.
Yeah, because usually, I mean, a lot of people actually told me they're gonna show up. So
Okay.
I think that's because maybe because of that people are not showing up. Let me just fix that.
Sure.
That's interesting. Hmm. Yes, all fair. There should be. Yeah, maybe we should wait for like a couple of minutes. What do you think?
Sure.
How's it going, Sifan?
Good.
How's your the double null? Sorry, the double sound Euler characteristic article?
Yeah, it's in very good progress. It takes longer than I expected, but it's in a
Mm,
very good shape. And I have a
nice, nice.
follow-up work.
Oh yeah. How is when is it coming out?
Sorry.
When is it coming out?
Oh, hopefully this year. Right.
Okay, good, good,
Yeah.
good.
Hello.
Hello,
Oh, how are
Master.
you doing?
Good to see you. How you doing?
Yeah, good to be part of this meeting. Yeah.
Of course. You're welcome all the time. Yeah, always.
Yeah, I was in the US for some time, but like a month ago, I spent a month in Washington, in the area of Washington, but not close to Cambridge, actually.
Ah, I see.
So you are still in Harvard. You stay for another year or two.
Oh, yeah. So this is basically my last semester. So I'm moving to Beijing.
Ah, okay. Will be
Yeah,
good.
it's close to home, and it's like
Mhm.
I thought, okay, like it might not be a bad option. So
Yeah, yeah, no, it would be good. A very huge group of people in GR. So.
yeah. Do you know Lars also moved there?
Hmm. Say again. What
La-
did you say?
Lars?
Oh yeah. Of course. Lars Anderson. He
Yeah.
he has been there. Yeah. Did you talk to him recently? Or
Yes,
I,
yes. I did talk to him like a few weeks
mm,
ago, and
okay.
you also have this Piotr Crucial. Do you know that? Like he also moved there.
Who do you say?
Crucial?
Oh no, I didn't know. When is that now? Or
Yeah, he moved
what?
there like last month, I think.
Oh, I see. Is it also a permanent position? He
I
probably retired. He has to retire from Vienna, so I guess.
Yes.
Mhm. Okay. I didn't know, but it's good. Yeah, people.
Yeah.
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 Uh, would be a good place for you to be.
So anyway, Sifan, okay, good to see you, Professor. Sifan, should we get started?
Yeah, sure. Let me share. Please enable me.
Yes. Yes, you can share now. Yeah.
Oh, can you see my screen?
Yes, yes. Right.
Oh, there you go.
Okay, good morning, everybody. Welcome to this week's GR seminar. This week, we're actually very glad to have Sifan from NUS, and he's going to talk about this really new and really exciting work, low regularity, local well-posedness for the elastic wave systems. So, Sifan, welcome, and please take it away.
Thank you, Pascal, for kind invitation and kind introduction. So today I'm going to talk about low regularity local well-posedness for the elastic wave system. So this is a recent work, a joint work with my colleague in NUS, Xinliang and Haoyang Chen. So so today let me do the opposite than usual. So usually people present their main theorem in minute 50, so let me present my theorem in minute 1. So here's the main theorem. Consider a solution to the admissible harmonic elastic wave equation. So let me hold this term a little bit, which is this admissible harmonic elastic wave equations is a special type of elastic, belongs to a special type of material, which we will spend a lot of time explaining why we use this equation and why we focus only on this material. Okay, so for this type of material, then you can split dynamics into 2 parts, so phi and psi. Well, let me use phi and psi to separate these 2 guys. So phi represents the divergence part, and the psi represents the curl part. So phi can be referred as the longitudinal wave or compression wave, and the psi can be interpreted as a transverse wave or shear wave in the physics or engineering literatures. So they satisfies the regularity assumptions. So basically, phi needs to be in H3 plus, and the psi is in H4 plus. So let me note that this phi in H3 plus is optimal, which I can provide a counterexample done by Xinliang and Haoyang and Sulu. So that's the first assumption. That's a regularity assumption on the Sobolev space for different parts of the dynamics. The other one is the image of data functions are contained in the domain of hyperbolicity. This is a very general assumption that basically is saying that we only focus on when a system is hyperbolic. Then the solution's time of classical existence can be bounded from below, and we can propagate the Sobolev regularity. So basically, we have solution phi lives in H4, and psi lives in phi lives in H3 plus, and psi lives in H4 plus for at least short time. In addition, phi and psi satisfy the following straight-cut estimates, and this is also the main tool that how we get the estimate 1. So the rest of the talk will basically mainly focus on to make sense this theorem. So I will tell you what are the admissible harmonic elastic materials and how we understand this special type of wave equations. So then the goal split into 3 parts. So I will introduce the standard elastic wave equations also, because I think the study of elastic wave equations has been relatively quiet in recent 20 years. So I will introduce the admissible harmonic elastic materials, which belongs to a subset of harmonic elastic materials. This special type of material was discovered by us, and we will explain why we focus on this material and give the excuse of why we are unable to consider a larger subset of elastic materials. if I have time, I can talk about the proof of low regularity local well-posedness of the materials that we focused. All right, so this is the plan for this talk. Any questions regarding the main theorem so far? All right.
This delta, this is the spatial derivative or a space-time derivative. This math BF. Sorry, the bold.
Oh.
Two. Yeah.
Yeah. The bold is for the space-time derivative.
Okay.
Yeah.
Okay. Thank you.
So generically speaking, if you have space derivative, you can replace it just by equations, wave equations. You can replace two-time derivative just using wave equations, which I will show you later, algebraically. All right. So let's talk about the setup first. So the material is assumed to be homogeneous, isotropic, and hyperelastic. These are very general assumptions. So for the example of rubber, then you have such properties satisfied. Okay, so the solution, or one of the solution, is motion, can be motion, and deformation gradient is defined to be the gradient of motion. And the most fundamental or central object that we need to study is the store energy functional, which we denote by W. W depends on the principal invariance of FF transpose. And this is called the Cauchy-Green string tensor. You can define it to be FF, a function of the FFT or a function of the FTF. It depends on you. Right. Once you have this energy store energy functional, then you can define your Lagrangian, which we showed in equation 3. Then you take Euler Lagrangian, then you can have something that looks like very suspicious to be like a quasilinear wave equation. And the structure of this W plays a main role here. And lastly, if you like, you can define displacement to be P minus X. This is very useful in the small data regime. So when you are in small data regime, when you define this displacement, then U and derivative of U are usually assumed to be small initially, and then you can propagate the smallness. But here you can either pick U or P be your solutions. So these are general setup. So if you express the Euler Lagrangian equations, then you can receive this equation. This is written in very non-specific way because this is just written when you split the dynamics that you have linear terms on the left-hand side, but and the right nonlinear terms on the right-hand side. So for the terms on the left-hand side, C1, C2 represents two wave speed actually, which you can see later on. So usually for all the materials that I know, C1 is strictly greater than C2. And the non-linearity can be very complicated, but one good thing is that it's this G is linear in D square of U. And this has much things to do with the energy store functionals. All right, and you see that the equation 5 is not a single quasi-linear wave equation, it's a quasi-linear wave system. So that increases the difficulty by a lot because you can think like on the left hand, if you consider the components of U, you can have two derivatives of U1 on the left, but you have two derivatives of U2 and U3 on the right. So in general, that causes a big problem. So let's talk about the standard local well-posedness. So you can rewrite the equation 5 in the following form in equation 6 and 7. So this this 4-index tensor can be viewed as the expression of nonlinear term G. All right, and then the box term is what you have on the left-hand side. So just like what you did for generic quasi-linear wave equations, for this quasi-linear wave system, you can do the similar trick by using energy method. Like Q capital Q and little q are quadratic forms in their first derivatives. And then you can replace V by derivatives of U so that you can have energy estimates, right? In this process, you need to assume that two derivatives of U, L infinity norm of two derivatives of U is bounded. Actually, you can assume less. You can just assume the L infinity in X and L1 in time norm of D squared U is bounded. That's one important thing. But standardly, in a classical way, you just assume this L infinity norm of dux is D squared U is bounded. So to make sense, this estimate 10, you need this guy to be bounded. That's why we need n to be greater than 3.7/2. Because in this regime, you can bound D squared U by Sobolev embedding. Right. So this is basically very similar to what's going on in the quasilinear wave equations, which we will give a review later on. So let me give some reference of the previous result in terms of addressing the elastic wave equations. So the first set of the results are local results with large data. So the local well-posedness was understood in the classical setting in 70s, and the EO-posedness for the solution in H3 was driven by the instantaneous shock formation in the work of Chen. So we have two levels, two thresholds. H3 is the threshold that solution may not be good, or solution may be EO-posed. And 3.5 is where the classical level stands, above 3.5. So when we talk about low regularity solution, we focus on the regularity level in between 3 and 3.5. So recently, there is a very interesting work by Lars Andersen and Lev Kapitansky. They focus on the so-called neo-Hookean material. So Hookean material give you the linear elastic equation, and neo-Hookean material is when you set this energy store functional to be your trace. So when you are in neo-Hookean regime, you just write this as trace of FFT. Right. So in this regime, they can prove local well-posedness below the standard level. They use a very different method than we are going to introduce today, but it's still worth mentioning that this is very interesting work. They define velocity instead of using U as solutions, they use velocity, which defined to be one derivative of U, and they restrict themselves in the Eulerian regime so that their velocity looks like the velocities in the Euler's equation. And then they define vorticities based on their definition of velocity, and they discover that the vorticity they have satisfies a first-order hyperbolic system, where they can apply Streetcar's estimates. That's why they can go below the standard level. So in their way of defining velocities, they actually have 4 velocities. So this problem also appears in our work. So it's like you not only need to define du over dt, you also need to define du over dx. Like you need the substitution for the deformation gradient. That's basically the short version of the story. And I'm not sure whether their result can be pushed down to the optimal level like H3 plus. Because in their work, they didn't dive too much into the geometry, which I will let you know why we need geometry to approach the H3 plus local well-posedness. But the interesting thing is that they discover the vorticity that they can apply Streetcar's estimate on it for this type of materials. the other set of the previous result I present here is global in time result with small data. So there is a very interesting connection between local result with large data and global in time result with small data just by self-rescaling, right? So it's worth mentioning some global result in short data, in small data regime. So we know that singularity will arise. Those singularities are basically shocks. And you can have almost global existence. Basically, the solution exists until the shock forms. If you assume null conditions, you can have global existence. So you can play around with the different materials and assuming different nonlinearities on your right-hand side of the elastic wave equations so that you can get some sort of null conditions. So this H3 Well-posedness level may not be the Well-posedness level for all the elastic wave equations. So that's one thing we need to be careful about. So maybe it is maybe conjectured that for some of the elastic wave equations, you can go below H3. All right. So now let me explain a little bit about the difficulties improving low regularity local well-posedness. So the first reason I want to tell you is that why the method in the small data results cannot be fully applied here. So in small data regime, they assume U and du to be small. Therefore, they can use not the full elastic wave equation, they can use truncated elastic wave equations so that their nonlinearity is up to quadratic, so they have nonlinearity up to du times d square u, right? So if you consider large data, you shouldn't drop all the higher order terms. For example, du square is worse than du when the data is large, right? So, but in their case, in a small data regime, they can just consider du times d square u at maximum. So that gives a huge advantage because now they can just Taylor expand the nonlinearity and drop every higher order terms. So, and they can put or manipulate the constant or coefficient of every nonlinear terms. That's why they can assume some null conditions just by assuming the coefficient in front of their nonlinearities. Right. So that's the main difficulties that we have. That is, we cannot use small methods from the small data results. Moreover, another reason that why we cannot use small data result ideas is that in their case, in the decay estimates and L2 infinity estimates, they usually require 5 to 10 derivatives. So that's not allowed here. The other difficulty is quite obvious for this quasilinear wave system where you have 4 indices. People just don't know a very generic way or very general way to understand this type of system. So we have very good understanding when you replace this A by box and you remove this J, right? We have a very good understanding when you have 2 indices, but not too much when you have 4 indices. And this is, physically speaking, is because of the deep coupling between characteristics with different speeds. So in particular, characteristics with different speeds can intersect or even intertwine. That means you don't have specifically a faster speed or slower speed if you are in large data regime. So that's one thing you need to be careful. And it's really hard to estimate the slow, to estimate on the characteristics when you have other characteristics putting effects on it. So let me briefly explain why I call it multi-wave speed problem. So naively speaking, we can just take divergence and curl of the elastic wave equations to get the equation 11. So this does not mean anything because you have 3 derivatives on the left and you have 3 derivatives on the right. But for the linear term, if you just ignore G, you just assume nonlinearity is 0, you can see that the divergence part and the curl part of the solution satisfy different wave equations with different wave speeds, right? So in the linear case, the divergence part strictly represents the faster wave because C1 is greater than C2, and the curl part represents the slower wave speed. But when you introduce the nonlinear term with large data, then the divergence part may not be the fastest wave, right? So that's one difference that we have with the work by Anderson and Kaputansky. They assume that the curl part satisfies the transport equation instead of the wave equation, based on what I understand. So so my goal to understand the elastic wave is using quasilinear wave knowledge from the quasilinear wave equations. So before we understand the multi-wave speed problem, let's understand the single wave problem. So if the wave equation looks like this, when the solution, when the metric depends on the solution itself, in the next page, we will have the metric depends on the one derivative of the solution, which is closer to what we have for elastic wave equations. But for this type of equation, now the standard regularity classical level is 2.5. And the first improvements start in 90s, where Bahari Shaman and Taru using Streetcar's estimates based on the Fourier integral parametrics representations, they can push the regularity below 2.5. And then Tataru improved the Streetcar's estimate to 2 plus 1/6. If you don't dive into geometry and purely use the indices in the Streetcar's estimates, and then 2 plus 1/6 is the optimal that you can get. So if you want to go below, you have to discover the geometry that is not only this solution satisfies a good quasilinear wave equation, but also the metric G satisfies the quasilinear wave equation connected to the Ricci curvature of this metric. That's a very interesting observation in the work by Kleinerman and Rodnyansky. And then they pushed the level to H2 plus for Einstein equations in the wave coordinates. And then the optimal level was reached by Smith, Tataru, and Wang using different methods. So in general, there are two methods. One is Smith, Tataru's method use a paradifferential approach. The other one is Wang's methods using the vector field methods approach. So in today's talk, I will focus on Wang's methods or the Kleiman-Rodnyansky's method using vector field method. So H2 plus is optimal is because we have H2 Well-posedness first brought up by Lindblad. And then this is for the quasilinear wave equations. So for special type of equations, or actually for Einstein equations, you can actually reach H2 level of low regularity, local well-posedness, but you cannot use wave coordinates. So if you use this regime, then H2 plus is the best that you can get. They use Yang-Mills frame so that they can prove bounded L2 curvature conjecture for the Einstein vacuum equations. So those are the results for the quasilinear wave equation when metric depends on the solution itself. When the metric depends on one derivative of the solution, well, there is actually a transform, then it's like you take one derivative of equation 13 and then you change variable such that phi is your new phi is your d phi, then you are in equation 12, right? So there is a change of variable thing. So basically it's telling you that everything here, everything for this equation can be moved to here, right? In some sense, but not completely. So including the fact that the classical level now is H3.5 because you change your variable d phi to new phi. So Smith, Tatalu, and Wang's level is now H3 plus. But a very special thing for this type of equation is that you can even go below H3, assuming you have good null conditions, or even better properties than just null conditions. So in the breakthrough by Ephraim and Tatalu, they consider the time-like minimal surface equation in Minkowski space, then they can go below H3, even though you can still got Well-posedness due to instantaneous shock formation at H3 level. So that is saying for some type of equations of the form 13, you can have Well-posedness due to the shock formation at H3 level. But if you assume better structures, you have a chance to go below H3. So the optimal level is H2.5 conjectured here. So we are still a little bit away from it. So I want to mention that there was no low regularity, low well-posedness result on multi-wave speed problems, but there are results on multi-speed problems, which I will tell you very soon. All right. So this is the multi-speed problems that I want to talk. So this is come from the compressible Euler equations and the relativistic Euler equations. So if you look at the equation 14, you have, first of all, 14a, you have a quasilinear wave equation of velocity v. And this is the vorticity of vorticity, which is kind of bad because now if you look at 14, you have two derivatives on the left and you have two derivatives on the right. So that requires you to find a better structure for this vorticity of vorticity term. But luckily for compressible Euler and relativistic Euler, you have 14b equation where the vorticity of vorticity satisfies a very good transport equation, which gain you a lot of regularity. So if you if you just count the derivative, you have three derivative of solution on the left because vorticity count should be counted as one derivative of the solution. But you only have two derivatives of the solution times one derivative of the solution on the right. So that's very good. You actually gained a lot of regularities. So this is the first thing that you need. One of the things that you need for proving low regularity, low well-posedness result for multi-speed problems. That is, you need to have regularity gain on both sides. So if you remove this vorticity term, then you actually have a regularity gain for 14a, and you have regularity gain for 14b no matter what. Right. So if you combine these two together, you can just close the argument just enough to give you a low regularity result when V is at the optimal level. So V is in Sobolev space H2 plus. That's the first thing that you need for multi-speed problems. The other thing is the certain level of decoupling exists. This is very clear in Euler equations. So for example, the transport part remain trivial if it initially vanishes. That is saying, if you set vorticity to be 0 at your initial data, then you actually Euler equations can be reduced to a quasilinear wave equations. In the meanwhile, vorticity and entropy gradient remain 0 until the shock forms. So there is a decoupling exists here. However, for the generic elastic wave equations, you don't have either property satisfied. So you don't have regularity gain on both parts. You don't have regularity gain on every single part, and you don't have decoupling. That is saying, if you have vorticity set to be 0 at the very start, and then the vorticity will occur no matter what in short time. Okay, so regarding the multi-speed problem that I just mentioned, for the non-relativistic case, if you put H2 plus assumptions on the wave part of the data, basically the velocity v, density, the entropy, and then you put H2 plus and Holder regularity of the transport of the data. Basically, the transport part is vorticity and entropy gradient. Then Disconzi, Low, Mazzone, and Speck prove that you can have well-posedness in this setup, local well-posedness in this setup. And Chen Wang did an improvement. She removed the Holder regularity for the transport part of the data, but you still need to, you need omega to be in H2 plus. So a very important takeaway here is that in order to prove H2 plus for velocity, you need H2 plus for vorticity. And remember the standard level, the classical level is H2.5. So in order to decrease the regularity on the velocity, you need to increase the regularity assumption on the transport part, because H2 plus for vorticity is like H3 plus for whatever the transport part of the velocity, right? So this is a very important takeaway. And it is still remain open whether you can go below H2. So the conjecture is H1.5 because it matches with the incompressible result. But I'm kind of negative towards that the fact that you can go below H2. For relativistic Euler equations, you can have a paralleled result and arguments. So in the earlier work by me, you can have H2 plus on the wave part and H2 plus and Holder regularity for the transport part, and also this transport part can be this Holder regularity assumption on the transport part can be removed. So let's first to understand elastic wave equations more. Let's first try to get some materials that satisfy the second properties that a certain level of decoupling exists. Right. Let's worry about this first. So the question is asking, can I have something in the elastic wave equations so that I can have similar things as what I have in the compressible Euler equations? The answer is yes. So to understand that, we need to first define the so-called pseudo-irrotationality. It's just like the irrotational thing for the compressible Euler. So then with this definition, we can call the material harmonic if and only if for such material, the pseudo-irrotational initial conditions in the absence of body forces always lead to pseudo-irrotational motions. So in short words, if the dynamic is irrotational at sigma 0, then it should be irrotational at sigma t for all t. Okay, for such material, we call it harmonic materials. And harmonic material is very important in engineering because it can, if you assume vorticity to be 0, then you are actually in the quasilinear wave equations, just like 13. Okay. All right. So the next question is about how can we define, or how do we classify the harmonic elastic material? So this is work done by Fritz John in the 60s. So the main idea is that you have some restrictions on the energy store functional W. So that W is Fr plus As plus Bt, A, B are constants, and F can be arbitrary function. And RST are singular values. RST are eigenvalues of, RST are principal invariants, and E1, E2, E3 are singular values of F. Okay, so this is an if and only if condition. That is saying, if you have harmonic elastic material, W should look like this, and if W look like this, then you will have a harmonic elastic material. So this is a very strong result. However, this harmonic elastic material seems not helping too much in our understanding, because provided non-zero vorticity for initial data, the divergence part and the curl part are still deeply coupled at top order level. So I just said before, if you assume zero vorticity for initial data, then you don't have curl part. You only have divergence part. So you have a quasilinear wave equations. But if you insert non-zero vorticity on your initial data, then the curl part and divergence part are still deeply coupled. So it is even worse than that. It is unclear whether the curl part can be written as quasilinear wave equations. So basically, you still get a quasilinear wave system like this. So you have ui on the left, but you have uj on the right, right? And j is not the same as I. Yeah, so the curl part still, you cannot, basically you still cannot separate the dynamics, especially for the curl part. You kind of can separate the divergence part out. That's what I'm going to introduce here. So here I want to restrict my scope to focus on an even smaller subset of the harmonic elastic material, which we call it admissible harmonic elastic materials. So first of all, equation 18 is just a rewritten the elastic wave equations. So no assumption is put at this stage. So we call a material admissible harmonic when the nonlinearity on the right-hand side of 18 satisfy this expression. So E is a function of du, should be G of function of du times identity matrix, and plus B times determinant of F times F transpose inverse. B is just a constant. All right, so the argument is that if this nonlinearity assumption is satisfied, then we can actually separate the dynamics of divergence part and curl part. But in order to do that, in order to introduce how we got the separated dynamics, I need to tell you the metrics with respect to different waves. So GE represents the fast wave. It's like a quasilinear wave. So G depends on one derivative of both divergence part and the curl part. And for the curl part, we have for the dynamics in curl part, this is kind of simple. We only have a linear term here, linear matrix here. So it does not depend on any of the solutions. So if we assume the nonlinearity that admissible harmonic elastic material required, then we can just take divergence and curl of the elastic wave equations to get this coupled equation 21. So the first equation is satisfied by the divergence part. So you see that we only gain regularity for the divergence part. If you count the derivatives, you still have you have three derivatives of phi on the left, but you have two derivatives times two derivatives of phi times three derivatives of psi on the right. So we actually lose derivative for the curl part in this equation. This is very similar to what's going on in the Euler equation. So if you go back to the Euler equation, you have here, you lose derivative in the divergence equation, in the divergence part equation of your curl part. So you have two derivatives of the divergence part equals to two derivatives of the curl part, right? So very similar thing happening here. So it is unknown that whether this phenomenon is generic, but we'll keep it like this. And for the curl part, the curl part that we consider satisfy a very good equation. So in particular, for admissible harmonic elastic material, the right-hand side is just 0. and the left-hand side is this H is linear, does not depend on D of psi, but we just put the D psi here and D square psi here just because we understand we can solve it as long as it's decoupled. So if you look at 21b, we can solve this system as long as you don't have phi in your 21b. So physically speaking, the shear wave do affect the longitudinal wave, but not vice versa in our setting. All right. So any questions so far before I talking about the strategies of proving local well-posedness in low regularity regime?
Maybe just a quick question. Can you define G capital E and H capital E?
Yeah. This is like
Okay, you show
the acoustical metric. Looks like an acoustical metric. Yeah.
Oh, okay.
Yeah,
Okay.
and this G prime is just the derivative of G with respect to its arguments.
Okay, sounds good.
Yeah, sure. All right. So any other questions? So now I have successfully reduced the complicated elastic wave equations into something that I can solve. So I have an elastic wave system, but I gain regularity on both parts, and the decoupling exists at a certain level. So now I can proceed of deriving low regularity local well-posedness for these two guys. So here is the dynamics, right? So the faster wave is the divergence. So the divergence part strictly represents the faster wave. So that's the hyperbolicity condition that we talk about. You need to put the initial conditions such that the divergence part is strictly the faster part, and then you can propagate this property for at least short time. So for at least short time, divergence part will remain to be the fast part. And the curl part here, I use flat cone because it's kind of trivial for its linear equations for harmonic elastic, admissible harmonic elastic wave equations. It can also be curved if you consider the equation 21b, which is a quasilinear wave equation. But as long as it's does not involve with the divergence part, and as long as it's the represents a slower wave, then we are fine. All right. So here is the general approach. So this approach was inherited from the low regularity problem for quasilinear wave equations. So we start with the bootstrap assumptions on the divergence part, and we can derive separate estimates, including energy estimates and the streetcar estimates for curl part, right? Because it's decoupled from the system. This is really important. If you have your curl part equation depends on the divergence part, then you will have big trouble. You are trying to control everything in one go, and this will require that the curl part, the equation of curl part gain more regularity of the divergence part. So what do I mean by that? Looks like, if you recall Euler, the right-hand side, you cannot have d square of phi. If you want to introduce phi, you cannot have d square of phi. You cannot even have d phi. You need to have phi here. Okay, you cannot even have d phi in the Euler case. In the work done by Chen and Dizanzi, Mazzone, Law, and Spec, you cannot even have d phi. You need to have phi here. Of course, we know how to do it when you have phi here, but it's not physical in the elastic materials. So we just put it to be 0 because this fits the computation we have for our material. So the idea here is that you need a separate estimate because it's decoupled, or we have a separate estimate because it's decoupled. But if it is coupled, then you need to have more regularity gains so that you can close everything in one go, in one big bootstrap assumptions. So once you have this ingredient ready, first thing that you want to do is do the energy estimates for divergence part on sigma t. So you need to do two types of energy estimates. So this one is on a flat or on constant time hypersurface. The other one is you want to do the conflux energy estimates because you want to estimate the geometry, which I will tell you very soon, mainly in order to get the decay estimates. And then you want to use these energy estimates to control the geometry. So basically, you want to control the metric G has good the first derivative and good part of the second derivatives. Then you use your geometric estimates to derive a conformal energy estimates to derive a decay estimates. Then everything else is very standard in the streetcar estimates in the of the quasilinear wave equations. So the colored box is where you need some new ingredient or new ideas in our particular examples or in our particular materials or equations. So due to the structure of the admissible harmonic elastic materials, basically we need to deal with the influence of the curl part into the divergence part. Right? We need to make sure that everything is fine, even though we lost derivative here and there, right? Okay, so let me do a quick review of streetcar estimates. So this was discovered in the 70s for linear wave equations. So you have a streetcar pair, rho PQ. If they satisfy 25, then you have the estimates 24. And moreover, if the equality holds here, then it's called endpoint streetcars. So basically, you only need to worry about endpoint streetcars because everything else can be derived by interpolation between endpoint streetcars and energy estimates. So if you look at the energy estimates, it's also a streetcar pair. It's I believe it's 0, infinity 2. So rho PQ equals to 0, infinity 2 is your energy estimates. So endpoint estimates was proven in Q tau by Q tau, and there is an exception. And unfortunately, this is exactly what we need. Right? 1 to infinity is exactly what we need in our case. So that's the story for linear wave equation. But if you put a nonlinear term here, can you derive the similar streetcar estimates? So there is intensively study. They were intensively studied in the 90s. So basically, streetcar estimates hold true if G is above C2. It will fail if you go below C2. But C2 here is way rougher than our case. So in our case, G is in H2 plus, right? So this was way too high. So so in general, streetcar estimates will fail in our setting. But how do people prove local well-posedness in low regularity regime using streetcar estimates? That's a very interesting idea introduced in those works. So the main idea is for these estimates, you don't want to prove it perfectly. You should allow some losses. So instead of proving d psi, you are proving d 1 minus epsilon psi. That's the basic idea. So you need to allow some derivative losses. Then you can actually show that you can prove streetcar estimates for d 1 minus epsilon for any small epsilon here, right? So basically, we want to prove the streetcar estimates like this. This will be our bootstrap assumptions, and it will be improved by these streetcar estimates. So for bootstrap assumptions, we have 1 on the right-hand side, but for the actual estimates, we have T star to the 2 delta on the right hand side. T star is the bootstrap time. So when the time is short, this is a strict improvement of our bootstrap assumption. So if you look like this, if you look at the Strickhardt estimates, the first term is the main term that we care about. The second term is mainly to used to prove the first term. So basically, if you check the Strickhart's indices here, it's basically what we have in the forbidden endpoint when dimension is 3, right? Okay, so there is a standard way of reduce these Strickhardt estimates to the decay estimate 20A. This will include a Duhamel principle and a partition of bootstrap time interval, so that this partition of bootstrap time interval depends on the frequency nu here. And by the Duhamel principle, you only focus on one time slab of your Strickhardt. So you do a frequency localized Strickhardt estimates, and then you use TT star argument that can reduce the frequency localized Strickhardt estimates to the decay estimates. And then you need to self-rescale with respect to a frequency. So this P1 is a Littlewood-Paley projection at frequency 1 because it's being rescaled. Before rescale, it's frequency P is frequency nu. Okay, so this may be a little bit confusing because the reduction process is quite long, but it's technical but standard. So now to derive decay estimates, we need to introduce geometry. So this is where the geometry plays a very important role. So this is standard null frame that people use all the time. So here, one thing we need to pay attention is that besides everything standard L bar U1 U2, we have V. So V is time-like H unit vector field of CU. So we are in multi-speed regime, multi-wave speed regime. So we have a faster wave which represents by metric G, and a slower wave represented by H. So we need to make sure H strictly represents the slower wave. That is saying we need to show V is time-like, right? So we actually need to show this. So it's important that the slower wave view this hypersurface as a space-like hypersurface, so that the energy is positive definite on this hypersurface for the slower wave dynamics. Okay, so once you have those null frame, you can have very standard null structure equations plus a decomposition of Ricci curvature tensor. So here, different to the Einstein equations, you have instead of Ricci equals to 0 or energy momentum tensor related terms, you have two dangerous terms that will not apparent in the Einstein equation in wave gauge. So this is D of gamma. Gamma is a contracted Christoffel symbol. This is very dangerous because now this is at the same level of your Ricci curvature. And if you replace box G of G, then you should pick up very dangerous terms like 3 derivatives of psi from 2 parts. First part is when box G falls on deep psi. You have no other choice because deep psi or psi itself does not satisfy any good equations, because box H psi satisfy good equations, not box G. So you can just view box G of psi as 2 derivatives of psi. There is nothing that we can do. So that's one source term that causes this very dangerous 3 derivative of psi term. The other one is when box G falls on phi or falls on phi, then because of the loss of derivative of the wave equation of the curl part in the divergence equation, box G phi will result to have 2 derivatives of psi So that's why box G falls on dphi, you will have 3 derivatives of psi. Okay, so this term basically is the influence of the curl part into the divergence part. Although it's the curl part is strictly slower wave speed, right? So I want to ask, how many minutes do I have?
Sifan, you can take like I think 10 minutes because we started like 10 minutes late. So
All right, thank you. So let me briefly tell you a very important but now very well understood result. So if you that is saying why the standard Morawitz estimate fails in this low regularity regime. So if you consider the standard Morawitz estimates, so you consider this. What's you need to control every term here. So Q is the energy momentum tensor and pi is the deformation tensor. So the most dangerous term in Q times pi is this guy. So it's trace chi minus 2 over R times L phi times L bar phi. Okay, so we are in the homogeneous wave equation regime because you already used the Duhamel principle. Now this term is bad because L bar phi does not have good decay or does not have sufficient decay. So the kind of looks like the only solution is to integration by parts of L bar derivatives. So you pick up L bar derivatives on trace chi and angular derivatives on trace chi, right? Because when L bar derivative falls on L here, then you can use wave equation to rewrite it. So you pick up these two guys. The last term is kind of good. Now you don't have a decay problem, but you have a regularity problem because you want to estimate not only the connection coefficients, but the one dangerous derivative of connection coefficients, right? So this is one of the reasons why you need to understand the expansion scalar or trace chi very well here, right? So that's basically give you the motivation why we need to control it. But here, you will have run into big problems in control L bar trace chi and angular trace chi. Let me give you an example. For example, you want to control angular trace chi. What you want to do is you just commute this equation, the Ricciardo equation with angular derivative. Then you will pick up angular derivative of Ricci. This is extremely dangerous because Ricci curvature only has epsilon differentiability. So you cannot take another derivative falls on Ricci, especially when derivative falls on this d gamma term. This will blow up the whole estimates. Basically, you don't have enough regularity on it because metric is only H2. So d gamma is H epsilon. So you cannot have another derivative falls on this guy. So it's very dangerous when you try to estimate angular of trace chi. But this problem was well understood. So instead of estimate trace chi, you estimate trace chi plus gamma L. So you just renormalize the Ricciardo equation. And then instead of estimating L bar of trace chi, you estimate the mass spec function. But you need to do more because this is actually involving a conformal change of the metric. So now the trace chi tilde is good after the conformal changing, but the conformal change constant is still very rough. You need to control the conformal change constant as well. So Chen Wang in his work, in her work, discovered very interesting equations that there is a secret connection between the mass spec function and the conformal constant. Right. Then the other things are quite standard, but still technical. You need to do two types of energy estimates, two types of conformal energy estimates. One is FRDR estimates. The other one is RP weighted estimates on the region away from the center, which I believe you guys know it pretty well. So lastly, let me spend some time talking about the difficulties that we have in addition to the difficulties inherited from the general quasilinear wave equations. So first one is multi-wave speed phenomena. So we need to control null flux. In particular, we need to control null flux of psi along Cu of G. So we need to control psi on the fast wave characteristics. That is equivalently asking we need to show Cu is space-like with respect to the slow wave metric. Okay, we need two things. We need a hyperbolicity assumption on the initial data, and we need to propagate it such that, okay, so this assumption is made on initial data such that Cu is space-like with respect to H. Then we prove it or propagate it using Strickard's estimates. The other one is we have lots of derivatives everywhere, basically, for our curl part, because the divergence part equation will suffer a loss of curl part. That's all know. And also from here, the Ricci curvature will very naturally lose one derivative in terms of the curl part. Right. So so we need to track the loss line by line, and we also need to control the second fundamental form K and Christoph symbol gamma, because in these terms they will involved with one derivative of the curl part as well, right? So when you control K and gamma, you don't lose derivative, but you lost derivative when you try to control the Ricci curvature, right? And controlling Ricci curvature is the main term. So this term contributes half of the main term of your Ricci curvature. So so to conclude and further moving on, so there are still some very interesting problems left open. So first of all, can we understand a larger subset of elastic wave equations? So we are restrict ourselves in a very narrow subset. So we restrict ourselves in a subset of harmonic elastic materials, which is also a subset of elastic wave equations. So we wonder whether can we do more than just that. The other one is optimal result on the curl part. So in our main theorem, or in our main result, we assume H3 plus on the divergence part and H3 plus on the curl part, which is kind of consistent with the Euler equations. But we want to ask the question whether we can lower the regularity assumption on the curl part. The other one is a description of a long-time behavior of elastic wave equations. So if you are in harmonic elastic material regime and you set curl to be 0, then it basically has no difference than the quasilinear wave equations, which is still very complicated, which is still not very well understood. But if you add the curl part dynamics, we wonder how the global structures will look like without null conditions even. Okay, the other one, the last one is the other multi-wave speed problems. So basically, for example, MHD or Einstein-Euler. So this result is the Well-posedness in H2 for MHD equations. So there is basically nothing known for Einstein-Euler, especially in the low regularity regime. So let me conclude my talk here and thank you for listening. And I'm happy to take your questions.
Thanks, everyone, for the great talk. So now is the time to take the questions from the audience. So if anybody has any questions, please unmute yourself and go ahead. Do we have any questions from the audience? I guess I'll ask a couple of questions. Sifan, so I think I missed. Can you go to that causal structure part when you do have the null cone? I think I missed that.
This one or
Yeah. So you have like yes. Before
yeah,
that, just go to the diagram.
yeah.
Yeah. Yeah. So I think I missed this part. Can you like explain me this fast and slow?
Yeah, so this is the null cone for the faster wave, right? So you need to control both divergence part and the curl part on this faster cone,
Yes.
or for this on this null cone. So you will have, so for the slower cone, for the curl part, you need to show that this cone is actually space-like,
Right.
right? It cannot be time-like. That is the equivalently saying that, asking that you need to show the faster wave is strictly the faster wave.
Yes.
Right, so this is the idea. So V is the time-like H unit vector field because so it's basically V is the normal in terms of metric H of this cone U. And it has to be time-like. You need to prove that.
Yes.
That's the idea. Yeah.
Yes. And what is the main difficulty? Like, what is the main obstruction of improving the regularity of the curl part? Is it that obstruction term in the Ricci curvature? I didn't follow that part.
Oh, okay. So the main difficulty is to control the geometry, I would say.
Yeah.
So controlling the geometry is important to get the decay estimates, as I just
Yes.
tell you here. Yeah.
Yeah.
So the main difficulty is, take an example of trace chi. So if you want to control angular derivative of trace chi, you commute angular derivatives here,
Yes.
and you have angular derivative force on Ricci LL,
Yes.
which is very bad because first of all, you have angular derivative force on these two guys. This is not acceptable because these two guys only have epsilon differentiability. So that's the first thing.
Right.
You need to do a normalization. So put these two guys on the left so
Right.
that the combination of gamma and trace chi is good. The other thing is you have loss of regularity on your curl part when you consider the box GG here.
Right.
Right, you have, when you express box GG, you have three derivative psi on the right. So Ricci curvature is rougher in terms of curl part.
Right.
Yeah, that's two main difficulties. Then this difficulty is inherited from the quasilinear wave equations. So in their work, Klein-Maronowski, they already deal with this problem. They did not solve it fully. Chen Wang solved it fully, but this problem, the loss of derivative on the curl part, is very new.
This is intrinsic to this elastic wave system. This
Yeah.
part. I see.
And moreover, you have deep psi everywhere. It's basically you have these terms entering your geometry, so you need to control these terms as well. That's one of the other reasons why we need to control cone estimates, cone energy on the faster cone for curl part.
Right. Wow. So this is in a sense like actually seems like more difficult problem than like Einstein equations.
Structure wise, yes, but in how deep that the Einstein equation is, I cannot say so.
Yeah.
Einstein equation was so intensively studied.
True. All right, so I don't have any more questions. Anybody else?
Yeah, could you say some words about the MHD system? You mentioned it at the end. I
Yeah.
think the structure is I don't know, more complicated, less complicated.
Yeah. Yeah,
feature,
that's a
right?
very good question. So first of all, MHD system has something very similar to to elastic wave equation. So first of all, the vorticity cannot be always zero. They can create a vorticity from nowhere. The other thing is MHD is even more complicated because it's like three types of wave. You have transport part and you have two wave parts, right? So in my understanding, it's more complicated, and moreover, you cannot So one big disadvantage of MHD rather than elastic wave is that you cannot play with the nonlinearities. For elastic waves, you can just assume different types of materials, then you can maybe have a chance to get a better regularity or better null structures or better structure in general. But for MHD, it's kind of like a fixed system that you cannot play anything around it. And it's actually matched the hardest. So MHD is as the same difficulty as the hardest elastic wave equations with every nonlinear term appear. Yeah, that's my take. So I think it's very far than beyond understood.
It's still open to do the same as what you presented, right? For MHG, it's
yeah,
open.
Yeah, it's completely open. So you cannot go below a little bit. So we reach optimal result for the divergence part. And for MHD system, you cannot even go below the classical level. Okay. And the long-time dynamics of MHD is not very well understood based on my understanding.
Okay, thank you.
Great. Any more questions from the audience? If not, we might as well just stop the recording.